My name is Yago, and today, I'm presenting this work that basically exploiting a future galactic supernova to probe neutrino magnetic moments. So it's basically like what is the impact of non-zero neutrino magnetic moments in future supernova neutrino detection. Okay, so I'm from Unicamp also, like Pedro, and my collaborators in this paper is Subictiana and Manibrata Sen. So neutrinos, they don't have coupling to photons. They have no charge in standard model and many theories beyond standard model, but quantum loop corrections can induce electromagnetic properties. And one of these properties is the magnetic moment, okay? That is like an interaction here for Majorana neutrinos. We have a neutrino coming in, it changes helicity, so it becomes an antineutrino, and it has the effective coupling to photon. So we are going to see what is the impact of that interaction in the core collapse supernova. I'm not going to explain again what is a core collapse supernova. So you saw in the lectures of Shashank and the Dean also. But basically, I just want to say that during a core collapse supernova, during like 10 seconds, all types of neutrinos are emitted and huge number of neutrinos are emitted, okay, during 10 seconds. I'm just going to explore today the first 30 milliseconds after core bounce, that is called the neutronization burst phase. So in this phase, a huge number of electron neutrinos are emitted. So you can see here that before 50 milliseconds, the luminosity of electron neutrinos has a peak. This is the neutronization peak. And these neutrinos come from the electron capture on protons, okay, in the environment. And if you integrate the number fluxes of neutrinos until 50 milliseconds, you get like much more electron neutrinos than all the other flavors. These are, the red one is electron antineutrinos, and the blue represent all the other flavors. So having the initial spectrum, we can evolve it, okay? We can compute its flavor evolution and see what's the final spectrum and see what would be the signature of magnetic moment in supernova neutrinos. So first we assume there are transition magnetic moments for Majorana neutrinos, okay? So neutrinos evolve according to the 6 by 6 evolution equation, in which this like nu is a 3-position vector, one for each flavor, the same for nu bar. These Hamiltonians are the usual matter Hamiltonians for neutrinos. So as you can see here, these are the MSW potentials that you saw in the lecture of Kopp, Joachim Kopp yesterday. Okay, and the new thing here are these off-diagonal elements that, in addition to, okay, so these Hamiltonians will give conversion between neutrinos and between neutrinos among themselves and antineutrinos among themselves. And the off-diagonal elements, that is the magnetic moment times the magnetic field, will give transitions between neutrinos and antineutrinos. So, so that will be the signature: neutrinos converting to antineutrinos. Okay, so this is the matrix of magnetic moments. Due to technical reasons, like we don't have elements, so the diagonal is null, so we don't have intrinsic magnetic moments, but we have transition. So they mix the two flavors. And this is how we parameterize the magnetic field, okay? So the B0 is the magnetic field at the surface of the iron core here. And we are going to define it later. And that R0 is the radius of the iron core. And yeah, so we have the magnetic field profile. And this is the matter profile. So we need also the electron number density and other things to compute. So this is the matter profile, okay? This is some other quantity that has to do with the matter profile, and these are going to be used to compute the position of the resonances. So we have the MSW resonances that come from the MSW potential. I don't have much time to describe it here, but basically the idea is if you have a slowly varying matter density, there is a proper definition of what is slowly here, but I will not tell what it is. So if you have a slowly varying decreasing matter density, and you have an initial flavor state that coincides with a matter eigenstates because the density is very high, okay? These matter eigenstates propagate as, for example, here nu e, and as it reached the resonance, it changed so it changed to some other flavor, for example, new mu, and so you can have total conversion between new E and new mu, and that is something that happens for solar neutrinos, and that happens also for supernova neutrinos. Okay, this picture is taken from Junki book. I forgot to put the reference. So, and they make conversions between neutrinos and between antineutrinos. They don't cross between neutrinos and antineutrinos. But here we also have, in addition of the two resonances, two MSW resonances that happen in supernova, we have 3 resonant spin flavor conversion, okay, in which we have conversion between neutrinos and antineutrinos. So as you can see here, to compute the position of this resonance, we use this red line, okay, with this quantity, and the other quantity is used to compute the MSW resonance there, so whole times. So this is another way of writing this whole over m times y is the other way to write the electron number density. So when you put everything together, so you have 5 resonances. You have to compute the transition in all of these. So these are the level crossing diagrams. You can compute the final fluxes using this plot of the energy eigenvalues and how they vary in the density profile. Okay. So it turns out that although we have 5 resonances, it becomes very easy because everything depends only on this specific one that is a spin flavor high. So on the probability that at spin flavor high, the probability of conversion, okay, and all the others are fixed. So both the MSW resonances, they convert 100%. The other 2, the spin flavor L and E, they don't convert anything. So, and everything is dependent only on pH. So we can write, so see if there is no conversion here. So if this resonance H is non-adiabatic, this is 1, okay? These cancels and we have only the MSW standard fluxes as expected. But yeah, if this is different from 1, then you can have plus minus some term that depends on the initial fluxes. This is done for normal ordering. You can do the same for inverted ordering. Yeah, so basically we are going to probe how these fluxes are going to appear in 2 upcoming neutrino detectors. That is DUNE. Okay, DUNE detects electron neutrino by interaction with liquid argon, and Hyper-K detects anti-electron neutrinos via inverse theta decay. So when I say DUNE, I'm saying nu E, and when I say Hyper-K, I'm saying nu E bar. That's all necessary here. And yeah, so these are the results for normal ordering. In DUNE, what happens is like you have an initial peak of electron neutrinos. So you expect a lot of electron neutrinos coming to Earth. But if you include magnetic moment effects, so instead of the black curve, you get the blue curve. So you have a suppression of electron neutrino events in DUNE for higher energies, and enhancement for anti-electron neutrino events in Hyper-K at high energies. Okay, and so we start to see a difference. So this blue is the maximum effect that magnetic moments can cause to supernova neutrinos. For inverted ordering, it's even better. So you see at low energies now, you see that, I mean, for example, in Hyper-K, instead of getting like 500 events, you can get 1500 events. So this is the maximum effect. So that's why for Hyper-K inverted ordering, we will be able to be very sensitive, much more than for other experiments. So there is a enhancement for Hyper-K for anti-nu E, and suppression for nu E in DUNE, inverted ordering. Okay. Yeah, so we can make a chi-square, like we can assume that the null hypothesis is the true one, and so it's our fake data. Then we can perform a chi-square and see what would we exclude. So what are the sensitivities in case we have the next supernova when DUNE and Hyper-K are operating. And so if the true hypothesis is the magnetic moment null, and we put B0 equal 10 to the 10 Golf, like in Futini lecture she showed for neutron stars and a galactic supernova, we get these values. So everything of the order of 10 to minus 13 or 14 Bohr, in terms of Bohr magneton. Okay. So for you to see that these would be very interesting, so I put this in context. So all the measurements so far, they are able to probe at maximum 10 to minus 12 for astro observations, and the terrestrial experiments are at most 10 to minus 11 Bohr magneton. These are our results. We are able to probe a bit deeper, okay, for Dune and Hyper-K, so of the order of 10 to minus 13. But yeah, still we are very far from probing all the parameter space, let's say, for all possible models of neutrino magnetic moment. Okay, but this is an improvement, and if we increase the value of B0, that it's possible. I mean, for 1 order of magnitude, you decrease here for 1 order of magnitude. So depending on the magnitude of the magnetic field in the supernova, we can also get better results. The summary of these models is in that paper above. Okay. Yeah, so it's in ending. So there is some other thing that is interesting, like, so we are probing all the space above 10 to minus 14 Bohr magneton. In this region, neutrino, if we detect a magnetic moment signal in this region, neutrinos are probably Majorana. Otherwise, they would have two large masses. So if they were direct, they would have 2 very large masses. So it's excluded. So if we detect this signal, neutrinos are probably Majorana. And if we remove the photon line from that first diagram, we get a mass term. So by studying the value of the magnetic moment, we can also study the mass generation mechanism for neutrinos. Okay. So these are the conclusions. So basically the takeaway message is, when you have spin flavor conversion plus MSW conversion, you make nu E convert to nu E bar. So you suppress nu E, you enhance nu E bar. This allows us to put, in case of future detection, better constraints. The best constraints so far would be from this supernova neutrino detection. And I think most importantly and deep, we can study neutrino nature and its mass mechanism by seeing this spectrum, studying the spectrum of supernova neutrinos. Yeah, so.
So could you go back to your spectrum as a function of the energy, please? So here you have integrated in time, right?
Yeah.
But for the whole time period, not only for the neutronization peak, right?
For only the neutronization peak.
But then, I mean, nu E bar is much smaller, right? I believe, right? The nu E bar in Hyper-K. I mean,
in Hyper-K.
Okay, you have a conversion. Okay.
Yeah, so
this is the conversion between.
This is the usual case.
Yeah.
So then it increases a lot if you have magnetic moment.
Okay, yeah. No, but I was thinking in the standard case.
No, yeah. The standard case, it's much smaller. You are right.
Instead, in Dune, you have nu E's, right?
Yeah, in Dune I have nu E, and it actually decreases. So you expect like 30 events here, and you get like less than 15.
Yeah, but so, I mean, in the case of nu E's, in the normal hierarchy, the neutronization peak is greatly reduced, right? In the standard case, right?
It's what?
Is much reduced in the normal hierarchy.
Yeah, but you get even more reduced. I mean, it's much reduced compared to the initial flux, but still get the neutronization peak in your detector. Yeah. But you reduce even more if you include magnetic moments. Yeah.
Okay. Thank you.
Yeah.
And yeah, there's one question here in the on Zoom. Ibrahim, can you please? Go ahead.
Do you think the Juno can also probe, constrain on their neutrino magnetic moment measurements?
Who? Which experiment? Juno.
Juno.
Yeah, Juno can. I think so, because Juno will detect all supernova neutrinos via inverse beta, I think. So it would be very much like Hyper Kamiokande. So, did you hear?
Yep. Okay.
So yeah.
Okay. Okay, yeah, so unfortunately we have to move on. Thank you very much, Yago. And